Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it. This is chapter 8.6, so chapter 8, section 6, which is numerical integration. Now, in here, essentially, there are some definite integrals that are not easily that you cannot easily integrate them. However, that doesn't mean that we cannot figure out an approximation for them. And here, that's essentially what this numerical integration is going to do for us. It's going to allow us to find an approximation for definite integrals without having to actually integrate. So here we go. We have first something called the trapezoidal rule. The trapezoidal rule. And as the name would imply, this is based on trapezoids, all right? So in here, we're going to start with let f be continuous on the closed interval AB. All right. Then we get the following. Then the integral from a to b of f of x dx would be approximately b minus a over 2n times f of x naught plus, plus 2 f of x of 1 plus 2 f of x of 2 plus 2 f of x of 3, so on and so forth, until we get to plus 2 f of x of n minus 1 plus 2 f of x of n. Alright? And that's what that integral will be approximately equal to. And here, well, n represents the amount of intervals that the interval AB is broken into. Another way of saying this is n is the number of trapezoids that we'll be using on here. Alright? So the first thing that I want you to note here is, so I'll make a note here. This pattern, look at the coefficients. 1, 2, 2, 2, 2. Ooh, this last one's wrong. That last one should be a 1. Alright? Sorry. So it's 1, 2, 2, 2, 2, 2, 2, all the way up until the last one, where it's just 1. So 1, 2, 2, 2, all the way up until the last one, which is just 1. So the coefficients of all the insides is just 2. Alright? So let's see why we would want to do something like this. And let's get a visual for this. And we're going to compare this to rectangles. Alright, so here we go. Let's say that I had this curve, right? Where here's A and here's B. Alright. Now in this curve, what I'm going to do is I'm going to split this into a couple of intervals. Let's say that I have 1, 2, 3. Alright, so in here we're going to have these rectangles. Alright, now the idea here is that the sum of the area of these rectangles is pretty close to the actual area under the curve. But with trapezoids, and I'll use the same function, we'll also have the same amount. So 1, 2, 3. But if I draw trapezoids in here, right, I end up with a better approximation under the curve, because the actual distance here, the actual room that's left under the curve is even smaller now, right? That area that I colored in is a smaller region now, even though it is the same curve. So in here, the trapezoids essentially allow us to get a closer and closer approximation. So another way of saying this is that as n goes to infinity, the amount of, in this case now, trapezoids, the amount of trapezoids going to infinity, what we end up with is that formula, which I'm going to copy and paste it just to not write it again. This formula is going to be equal to it's going to become closer and closer to just that original integral. All right. And here we don't care about these anymore. All right. So that's the general idea. All right. The idea here with the trapezoid rule is that we're going to be working with trapezoids instead of rectangles. All right, because it is a slightly closer approximation than with rectangles. All right. So let's see what we get here. Let's start with use the trapezoid rule to approximate the integral. And here in example A, I'm going to say we're going to have the integral from 0 to pi of the square root of sine of x dx. And in here, I do have to tell you how many trapezoids we're going to use. So I'm going to say here with 4 trapezoids. All right. So here we go. So the very first thing I need to do here is I need to look at this interval. All right. So we're going from 0 to pi. And I want to split that up into, I want to use 4 trapezoids, so I need 4 intervals. And in here, well, this is going to give me, this is pi over 4, this is pi over 2, this is 3 pi over 4, and then we've got pi. All right. So now, in here, those are going to be my x naught, x of 1, x of 2, x of 3, and x of 4. All right. So that's something to keep in mind. We will come back to that in a little bit. Now, the next thing that I want to do here is, well, I want to figure out, well, let's look at the formula. We had a b minus a over 2n. So we need to figure out what that is. So in here, this is b, this is a. So what we have here is pi minus 0 over 2 times n is 4. So here I end up with pi over 8. So what I get now is that this integral is going to be approximately pi over 8 times, well, what was the formula? It was 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1, right? The first one's a 1, the last one's a 1. Everything in the middle is just 2's as our coefficients. So I'm going to have f of 0 plus 2f of x of 1, which is pi over 4, plus 2f of x of 2, which is pi over 2, plus 2f of x of 3, which is 3 pi over 4, plus 1 f of pi, the last one, right? Remember, the first one and the last one are 1's. Everything else in the middle is 2's. So what I get here now is we end up with pi over 8 times f of 0. So it's going to give me the square root of sine of 0, right? Because that was the function I was working with, right? Here's my function. Plus 2 times the square root of sine of pi over 4. Plus 2 times the square root of sine of pi over 2. So on and so forth. Square root of sine of 3 pi over 4, and finally just the square root of sine pi. Now, at this point, we're going to say let's evaluate the inside of each of those square roots. So sine of 0, 0. Sine of pi over 4, that's radical 2 over 2. Sine of pi over 2, that's 1. Sine of 3 pi over 4, that's radical 2 over 2. And finally, sine of pi, that's 0. So let's combine like terms now. Well, this 0 goes away. This 0 goes away, right? The square root of 0 is just 0, so that's gone. So what do we have left? And here I'm going to say, well, we still have this pi over 8 left. I had this expression. Let's actually look at that expression for a second before I start writing things here. And I'm going to do it in a different color, because I have this expression twice, right? That radical. So let's see what that is. So we have the square root of the square root of 2 over 2. This is saying 2 to the 1/2 over 2, and all of this to the 1/2. So this is really saying 2 to the 1/4 over 2 to the 1/2. If I want to rationalize this, I need to multiply by 2 to the 1/2 over 2 to the 1/2, which gives me on the bottom just 2, and on the top 2 to the 3/4, right? Just add the exponents. 1/4 plus 1/2 is 3/4. All right. So that's just that radical. And I can rewrite this now if I wanted to as the 4th root of 8, all of this over 2. All right. So what do we get? Let's go ahead and rewrite this line. So we still have that pi over 8 on the outside. In the inside, I have 2 times, I'll write it as 4th root of 8 over 2, plus the square root of 1 is just 1. So we have here just plus 2, and then plus 2, and again we have that 4th root of 8 over 2. These 2's cancel out, these 2's cancel out, so I get here pi over 8 times the 4th root, that was supposed to be the 4th root, the 4th root of 8 plus 2 plus the 4th root of 8, giving me inside this inside here, this just reduces to being, so we have pi times 2, well, yeah, 2 plus 2 4th root of 8 over 8. But then I see that both of these two terms in here have a 2, so I can factor it out. So I have 2 pi times 1 plus the 4th root of 8, and all of this over 8. Giving me now that this is going to be pi times 1 plus 4th root of 8, and all of this over 4, right? Because the 2 and the 8 reduce. So again, in there, that last part was just essentially simplification. But really the pattern again is what you need to remember. 1, 2, 2, 2, 2, all the way up until the last one, which is 1. Just the first one and the last one are 1s. So this was with 4 trapezoids. Let's do it again, but with 6 trapezoids. All right. So we're going to do the same exact problem. Now we've got the integral from 0 to pi of the square root of sine of x dx. In this case, we're doing it with n equals 6. In other words, 6 trapezoids. So here we go. What do we get? What we're going to get here is, well, we need to start off the same exact way. I'm going from 0 to pi, splitting this up into 6 pieces. All right? So there we go. And here we have pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, which is pi over 2, 4 pi over 6, which is 2 pi over 3, and finally 5 pi over 6 in there. These are going to be my x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, and x of 6. Alright? Now, in here, we also still need to do the b minus a over 2n. In this case, this is pi minus 0 over 2 times 6, which is pi over 12. And now, we get that this integral is approximately equal to, well, this thing, pi over 12, right, b minus a over 2n, times the, well, f of x naught. But x naught was 0, so f of 0 plus 2 f of pi over 6 plus 2 f of pi over 3 plus 2 f of pi over 2 plus 2 f of 2 pi over 3 plus, I'll write it down here, 2 f of 5 pi over 6, and finally plus f of pi. Alright? So what do we get there? Well, this pi over 2 is still just pi over 2. Pi over 12, excuse me. This pi over 12 is still pi over 12. And in here, f of 0. So in here, this is our function. So I've got the square root of sine of 0 plus 2 times the square root of sine of pi over 6 plus 2 times the square root of sine of pi over 3 plus 2 times the square root of sine of pi over 2 plus 2 times the square root of sine of 2 pi over 3 and plus 2 times the square root of sine of 5 pi over 6 plus the square root of sine of pi. Alright? And in there, well, what we're going to say now is, let's evaluate this. So we have that pi over 12 still on the outside times sine of 0, 0. So I have the square root of 0 plus 2 times the square root of sine of pi over 6. This is where the unit circle comes in really, really handy, right? So sine of pi over 6 is 1/2 plus 2 times the square root of sine of pi over 3. Sine of pi over 3 is radical 3 over 2 plus 2 times the square root of sine of pi over 2. Sine of pi over 2 is just 1 plus 2 times the square root of sine of 2 pi over 3. That is radical 3 over 2 plus 2 times the square root of sine of 5 pi over 6. Sine of 5 pi over 6 is 1/2. And finally, plus the square root of sine of pi. Sine of pi is 0. So I get here now pi over 12 times, well, the zeros are going to go away. Let's see what we can combine here. I see that I have this 2 square root of 1/2 and 2 square root of 1/2. That's going to give me 4 square root of 1/2. Alright, what else do I see? I see that I have 2 square root of radical 3 over 2 and 2 square root of radical 3 over 2. That's going to give me 4 square root of radical 3 over 2. Alright, and lastly, I see here I still have the square root of 1. So the square root of 1 is 1 times 2 is just 2. Alright, so now we've got two statements there in yellow and blue that we should rewrite. So I'll do it here on the side. The square root of 1/2 is just 1 over radical 2, which is just radical 2 over 2. Alright? Now, the square root of radical 3 over 2. Well, that's going to be 3 to the 1/2 over 2, and all of this to the 1/2, which gives me 3 to the 1/4 over 2 to the 1/2. If I multiply this by 2 to the 1/2 over 2 to the 1/2, well, what do I get? Well, I can't really combine those two on top there, but the bottom ones I could combine, so I just get 2. But on top here, these two, well, I'm going to get radical 2 times the 4th root of 3. All right? Now, at that point, well, let's see what we get. We have this pi over 12 out here times 4 times this radical of 1/2 was radical 2 over 2 plus 4 times this radical of radical 3 over 2. Well, that was this statement over here. All right. Actually, let's rewrite that a little bit more. No, I guess I really can't. Now it's written. So I'm gonna have here radical 2 times the 4th root of 3 over 2, and then that plus 2. All right. So at this point, what we see now is that some of the stuff reduces, right? So this pi over 12 still out here. This 4 and the 2 are going to reduce. This 4 and this 2 are going to reduce. So I end up with 2 radical 2 plus 2 radical 2 4th root of 3 plus 2. And what I'm going to say there is this becomes, well, I see that all of these have a 2, so I can factor out a 2. So if I factor out a 2, I end up with 2 pi over 12 times, I'm going to write this as 2 to the 1/2 plus 2 to the 1/2 times 3 to the 1/4 plus 1. All right. The last thing that we can really do here is we can write this as pi over 6 times 2 to the 1/2 plus 2 to the 1/2 times 3 to the 1/4 plus 1. All right. So that is the trapezoid rule. All right. So now let's talk about another way of approximating numerical integration, which is called Simpson's rule. All right. Simpson's rule. And this is what Simpson's rule says. Let f be continuous on the closed interval AB. And let n be an even integer. All right. It is very, very important that we have an even integer here. All right. So Simpson's rule for the following is, so we end up with the following. The integral from a to b of f of x dx is approximately equal to b minus a over 3n. Notice it's a 3 there now, before it was only a 2. So b minus a over 3n times f of x naught plus 4 f of x sub 1 plus 2 f of x sub 2 plus 4 f of x sub 3 plus 2 f of x sub 4 plus so on and so forth until we get to the second to last one, so 4 of x sub n minus 1 plus f of x sub n. All right. Notice here the pattern. Before, for trapezoid rule, we had the pattern of, so note, before the pattern was 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1, right? Everything in the middle was 2s, except for the first and the last one. But now, everything in the middle is alternating with 4s and 2s until we get to the second to last one being a 4, and then the last one is a 1. All right, so the first one's a 1, the last one's a 1, the second one's a 4, the second to last one's a 4, the third one's a 2, the third to last is a 2, so on and so forth. All right. Now, in here with Simpson's rule, what we're actually doing is we're approximating a function using uh, parabolas, essentially. All right. I won't go over the derivation of this, but let's say, for example, that I had something like this. Let's say that I had this something like that, right? And here's our interval from A to B. So what we can do here is we can use parabolas that split up into this interval. So let's say that I have this first parabola. Well, let's say that this region right here approximates that parabola. And let's say this next region right here is approximately that parabola. And let's say that this last region over here is approximately this parabola. All right. Um, and there, again, so essentially what we're doing is we're using these parabolas to figure out the area underneath these curves, right? So we're splitting it up here at these regions, all right? And again, the curve there is in blue. Perhaps I'll make that a little bit more clear. So we have here, this is our function in blue, and in yellow is our approximation. So now, again, we're using parabolas to approximate this. So let's do an example here. I believe I'm at example C. And C says the following. It's got, so it says use Simpson's rule to approximate the integral. All right. And here we go. So this is C. And we're going to do the integral from 0 to pi of the square root of 1 plus cosine squared of x dx. Notice that there's nothing I can do to really integrate this because 1 plus cosine squared, that's not in trig identity, so we cannot rewrite that. And here we're going to do it with n equals 4. Alright, so first I need to split up this interval. Alright, and since we're going from 0 to pi and we're doing n equals 4, so here's 0, here's pi over 2, here's pi over 4, here's 3 pi over 4, and like before, these are my x sub i's. Alright, and now I need to figure out about my b minus a over 3n now. Right now it's 3n, and I get pi minus 0 over 3 times 4, which is pi over 12. Alright, so now I get that this integral is approximately equal to, well, pi over 12 times, and remember, the pattern was 1, 4, 2, 4, 2, 4, 2, alternating until I get to my last one being just 1, which is why it's super important that we have an even n. So we're going to have f of 0 plus 4 times f of pi over 4 plus 2 times f of pi over 2 plus 4 times f of 3 pi over 4 plus, well, our last one now is just f of pi. So we get now pi over 12 times f of 0. So I have the square root of 1 plus cosine square of 0 plus 4 times the square root of 1 plus cosine square of pi over 4, so on and so forth. 2, 1 plus cosine squared of pi over 2 plus 4 times the square root of 1 plus cosine squared of 3 pi over 4, and lastly plus the square root of 1 plus cosine squared of pi. And now, what does that give us? Well, we end up with pi over 12 times cosine of 0 is 1. 1 squared is 1. 1 plus 1 is 2. So I get the square root of 2. Alright, or again, cosine of 0 is 1. So next one, cosine of pi over 4. Cosine of pi over 4 is radical 2 over 2. So if I square that, I end up with, so if I square root this, I end up with just 2 over 4, which is 1/2. Alright? So let's keep that in mind. So I have 1 plus 1/2 on the inside. 1 plus 1/2 plus 2 times the square root of cosine of pi over 2. Cosine of pi over 2 is 0. So I have 0 squared plus 1, that's 1, plus 4 times the square root of, well, cosine of 3 pi over 4 is negative radical 2 over 2. Alright? But I'm squaring that. So I have negative radical 2 over 2 squared. Negative times negative is positive. The radical squared is just 2, and then 2 squared is 4, which is 1/2. So in there, I end up with 1 plus 1/2 once again. And lastly here, cosine of pi. Cosine of pi is negative 1. So negative 1 squared is positive 1, and 1 plus 1 is 2. So let's see what we get here. So we have pi over 12 times radical 2 plus radical 2, that's 2 radical 2. 4, well, in here, this 1 plus 1/2 is 3/2, right? So similarly here, that's 3/2. So I have 4 plus 4 is 8, so 8 radical 3/2 plus radical 1 is just 1 times 2 is 2. Now let's look at that radical 3/2 for a second. If I look at radical 3/2, that's radical 3 over radical 2, which if I rationalize this, in other words, multiply by radical 2 over radical 2, I end up with radical 6 over 2. So that's just that part there. So I really have here pi over 12 times 2 radical 2 plus 8 times radical 6 over 2 plus 2. The 8 and the 2 reduce. Notice now that everything here is multiples of 2's, so I can factor out a 2, so I end up with 2 pi over 12 times radical 2 plus 4 radical 6 plus 2. But the pi over the 2 and the 12, they reduce, so I end up with pi over 6 times radical 2 plus 4 radical 6 plus 2. Alright? Now we can go ahead and do this again with n equals any other even number, but the idea will be the same. The only thing that we need to consider really is how this is affected, right, when we add more, when we do this with a higher value of n. But now, I want to talk about something called the errors in these. So this is just a theorem. These are errors in approximating, so errors in the trapezoid rule and Simpson's rule. Right? And the thing here is that Simpson's rule and the trapezoid rule are just approximations, right? So there's going to be some sort of error. So let's figure this out. So this is what the theorem says. It says if f has a continuous second derivative on the closed interval AB, then the error E in the approximation, so the approximation of the integral from a to b of f of x dx, by the trapezoid rule is given by, so the absolute value of the error would be less than or equal to b minus a cubed over 12n squared times the maximum of the absolute value of f double prime of x, right? And this is assuming that x is in between a and b in the closed interval a and b, all right? Similarly, so that's for the trapezoid. Similarly, if f has a continuous, but now we're going to have fourth derivative on AB, then the error E in the approximating, so I should say in. So the error in approximating the integral from a to b of f of x dx by Simpson's rule is given by, and now we're going to have the absolute value of E is less than or equal to b minus a to the fifth over 180 n to the fourth times the maximum of the absolute value of the fourth derivative in that interval from a to b. All right. Now, as far as this course is concerned with me, I will not be testing you on the trapezoid, on the errors of the trapezoid rule and Simpson's rule. I will be testing you on the trapezoid and the Simpson's rule, but not in the errors. All right, it will not be an official question. That is not to say that it cannot be like as an extra credit question. All right, this should say the fourth derivative. There we go. So I could ask this as an extra credit question, but I'm also pretty sure that it's part of your homework on WebAssign. So here we go. Let's do an example here. Determine, and what letter am I at? I believe I'm at D, maybe? Yeah, D. So D. Determine a value of n such that the trapezoid rule will approximate the value of the integral from 0 to 1 of the square root of 1 plus x squared dx with an error that is less than or equal to 0.01. All right. So here's what we're gonna do. First, let's recall what the formula was for this error. All right, and since we're using the trapezoid rule, well, the error for the trapezoid rule says that the absolute value of E must be less than b minus a cubed over 12n squared times the maximum of the absolute value of f double prime of x. All right. So in order to do this, well, we need to first figure out what f double prime of x is. So let's look at this. We're given the function, right? We're given that f of x is equal to 1 plus x squared to the 1/2, right? That's from there. Well, then f prime of x would be 1/2 times 1 plus x squared to the negative 1/2 times 2x, right, by the chain rule. I'm going to rewrite this as now, well, this 2 and this 2 cancel out, so I just have x over 1 plus x squared to the 1/2, all right? So at that point, well, what are we going to do? I need the second derivative, not the first derivative. So what are we going to do? We got to take another derivative. And I'm going to use the quotient rule now, right, for this thing. So the derivative of the top, 1, times the derivative of the bottom. So it's going to be 1/2 times 1 plus x squared to the negative 1/2 times 2x minus, so that's hold on, I messed that up. I messed that up badly. That's not how the derivatives of the quotient rule work. Let's start it again. The derivative of the top, 1, times the bottom, 1 plus x squared to the 1/2. There we go. Minus the derivative of the bottom, 1/2 times 1 plus x squared to the negative 1/2 times 2x times the top, x. All of this over the bottom, 1 plus x squared to the 1/2 squared. All right, there we go. Now I did it correctly. Good job. Good job, me. So now, in here, this 2 and this 2 cancel each other out. So what do I have here, really? Well, I see here that I have a 1 plus x squared and a 1 plus x squared. So we can factor out a 1 plus x squared. So what does that give us? But when we factor these, we have to factor out the smallest of the two exponents. I've got a negative 1/2 and a positive 1/2. The smaller of those two is negative 1/2. What am I left with? Well, this 1 goes away. This 1/2, I started with 1/2, but I took out a negative 1/2. I'm left with 1. So I have here 1 plus x squared to the 1 minus, this is gone, this 1 plus x squared to the negative 1/2. That's what I took out, and I'm still left with an x squared. And all of this over, well, 1 plus x to the 1/2 to the second is just 1 plus x squared. All right. So now, in here, I see that I have 1 plus x squared on the numerator to the negative 1/2. So I can bring that to the bottom as a positive 1/2, but I already had a 1 there, a 1 as an exponent. So I can have here 1 plus x squared to the positive 3/2. In these brackets, the x squared minus x squared cancel each other out, so I'm left with just 1, right, because those canceled out. So that's my second derivative, all right? Now, what we need there, and again from the formula, we need the maximum of that second derivative in our interval, right? And what was our interval? The interval we were working with was from 0 to 1. So in here, the max of f double prime of x on 0 to 1, well, let's think about this, right? In here, this is a fraction, right? And we're plugging in positive values. As soon as I start plugging in any value into here, right, into 1 plus x squared, well, this inside becomes bigger than 1. No matter what value of x I plug in between 0 and 1, because I'm going to be squaring it and then adding, it's going to be bigger than 1. A number that's bigger than 1 to the 3/2 is still bigger than 1. So 1 over something bigger than 1 is going to become smaller than if this was just a fraction of 1. So what am I saying here? Let's say, for example, that if I had, so consider x being equal to 1/2. Well, then this fraction of 1 over 1 plus 1/2 squared to the 3/2, well, this is going to be, this fraction, this fraction is going to be less than if I just had 1 over 1 plus 0 to the 3/2, or 0 squared, all right? And it doesn't matter what fraction I put on there, it's still going to be a smaller, it doesn't matter what value I put into the x, the overall fraction will still be smaller than this. So this value over here is just equal to 1. So the maximum here on that interval is 1. All right. So now, what does that do for our formula? Well, in here, we're going to say, well, we need that the absolute value of our error, which again is less than b minus a to the third over 12n squared times 1, right? That 1, I got it from here. And perhaps we can replace the b and the a. We were going from, our integral was from 0 to 1. So in here I can write this as just 1 minus 0. All right. So we need our error to be less than that, right? But we were also told that we want our error to be less than 0.01. That was from the original question. Where is it? See? 0.01. So what we can do is, since our error is going to be less than this, well, let's just force this to be less than 0.01. All right? That's exactly what we're going to do. We're going to force this thing, we're going to force this statement to be less than 0.01 and solve for n that way. And by the transitive property, our error will still be smaller than 0.01. So let's see what we get here. 1 minus 0 is 1, 1 cubed is 1, and 1 times 1 is 1. So I get here 1 over 12n squared is less than this 0.01, that's 1/100th. So I'll write it as 1/100th. At this point, isolating the n squared, so multiply it by 100, so I end up with 100 over 12 is less than n squared. All right. So at that point, well, what are we going to say? Well, we're working, recall here what n is, all right, before I do the next step. N is a number, the number of trapezoids, right? The number of trapezoids. So because n is the number of trapezoids, n has to be positive. So what we can do here is just take the square root of both sides, and I end up with, well, the square root of 100 over 12 must be less than just n. In other words, n must be greater than the square root of 100 over 12. And again, technically from here to here, this is not normally the way to do it, but since we have to have n being positive, we can sort of overlook the fact that we would have, well, I'll write the correct thing. So in here, we actually have two, this thing splits up into two inequalities. This is the one equality. The other inequality would have been negative square root of 100 over 12 must be greater than n. All right, that would be the other inequality. But in this one, I won't care about it. All right, I won't care about it because there n just talks about negative values, so I won't care about that. But in here, the square root of 100 over 12, well, 100 over 12, they're both divisible by 4. So I get 25 over 3. Now the square root of 25 over 3, that is approximately 2.89, which tells us then, well, n has to be greater than 2.89, so n has to be equal to 3. So what does this tell us? This tells us that the minimum number of trapezoids so that the error is less than 1/100th, 0.01, is 3. All right. So that's how you find the error that you would need there. All right. And that is the end of 8.6. Real quickly, I want to mention something about 8.7. 8.7, I will not be going into detail, but 8.7 is called integration by tables. All right, integration by tables. Now, in here, what they're talking about is that, well, there's something called a table of integrals, right? And this would be in the back of your book. If you have the PDF version or the online version of the book, well, it would be um, towards the very, very end of the file, right? But in here, integration by tables, what they're saying is some integrals. So there are many integrals that fit very specific formats, right? And the great thing about that is that they have been solved. These formats have been solved, all right? And now I'll just do one very quick example as to what we're talking about here, all right? So, for example, um, let's do this integral. So if I have the integral from 0 to 2 of x over 1 plus e to the negative x squared dx. All right. Now, from the table of integrals that's part of this book, there's one that's number 84 that's written as du over 1 plus e to the u. And this gives us just u minus ln of 1 plus e to the u plus c. All right. So what we can do here in this one is, well, I can do a u substitution here, right? If I let u be equal to negative x squared, then du is negative 2x dx, right? Um, which tells me then that, well, I have an x dx there, so I'm going to just solve this as du over negative 2 is equal to x dx. The next thing is I need to change the bounds, right? When x is equal to 0, well, then u is also equal to 0. When x is equal to 2, well, then u would be 2 squared is 4 with a negative is negative 4. So what I end up with here now is the integral of, well, let's see what we have. Originally it was 0, now it's still 0. Originally it was 2, now it's negative 4 of x dx, which was du over negative 2. And on the bottom, 1 plus e to the negative x squared. So that's going to be just 1 plus e to the u. So really I have here negative 1 half integral from 0 to negative 4 of 1 over 1 plus e to the u du. But we don't like to have this smaller value on top. So I'm going to write this as positive 1 half integral from negative 4 to 0 of 1 over 1 plus e to the u du. And we already have an integral for that, right? Du over 1 plus e to the u. I already wrote that what it became. So what we have here is this becomes 1 half times u minus ln of 1 plus e to the u, and all of this evaluated from negative 4 to 0. When I evaluate that, well, what do I get? I end up with 1 half times plug in 0, 0 minus ln of 1 plus e to the 0, minus 1 half times 0 minus ln of 1 plus e to the negative 4. But where did I get that second 0 from? That's awful. That should be negative 4. There we go. So what do we get? Well, here, let's think about this. E to the 0 is 1. So what I get here is 1 half times negative ln of, well, 1 plus 1 is 2. So 1 half 1 half times negative ln of 2 minus, let's simplify this inside first. Actually, there's not much to simplify there. So let's just distribute that negative 1/2. Negative times a negative is positive. 1/2 times 4 is 2. Negative times a negative is positive. So I have 1/2 ln of 1 plus e to the negative 4. Right? And again, this was just from using um, this pre-solved formula for this kind of integral. All right. Now there's many integrals out there like this that have already been solved for you. All right, and where you can just go ahead and use this kind of idea to solve it, where you just plug it in. But the one thing that you have to make sure is that whatever you think your u is, you definitely have the du on top. All right, or something, or a constant multiple of that of it. Right. That's what I was doing here when I solved for the du. I wanted I wanted to make sure that I did have a constant multiple of that du somewhere. All right. All right. So again, that's 8.7. I'm not going to go over 8.7 in any more detail than what I just did right now. All right. But you should be able to use the table of integrals to be able to apply it to your own problem if you need to. All right. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.